again, but maybe sometime in the near future. So I wanted to talk today about some of the work my group has been doing in a number of different areas, including some connected to machine learning. This is a fairly recent one of our group meetings. I don't have everybody in the group on this shot, but I've got most of them anyway. And today I'm going to be talking about some of the work in particular that Ruhi has been doing in couple cluster response theory. Ben Payton has been doing in machine learning, and my former postdoc, Roberto Di Remigio, work that he did in couple cluster Monte Carlo. I also mentioned that I have a wonderful set of colleagues in theoretical chemistry here at Virginia Tech. Most recent addition to our theory sector is Valerie Wellborn, who works on biological interfaces and complex environments. Some of you may know Nick Mayhall, who also does ab initio quantum chemistry, but he's also made a really fabulous name for himself in the ever-growing domain of quantum computing. Diego Troya, who does gas surface molecular dynamics and nanoscience. And of course, everybody here knows Ed Valeev, who I think is going to be speaking tomorrow. And I think Ed's here today on also doing ab initio quantum chemistry and explicit correlation and massively parallel quantum chemistry. I'll also, before I get into this, mention another major project that we've been involved in for some time, and this is the Molecular Sciences Software Institute. Some of you are already familiar with this. The MOLSI, as we refer to it, was launched just over 4 years ago, funded by the U.S. National Science Foundation. The Institute's headquarters are here at Virginia Tech in Blacksburg, Virginia, but it's a collaborative effort among 8 different institutions, including Rice, Stony Brook, UC Berkeley, Rutgers, Southern Cal, Iowa State, and the University of Michigan. This is part of the NSF's commitment to the White House's National Strategic Computing Initiative. And the fundamental purpose of the MOLSI really is to serve and enhance the software development efforts of our broad field of computational molecular science, not just the quantum chemistry domain, but also computational materials science and biomolecular simulation. So a very wide audience. The MOLSI has a number of important components. The heart of the MOLSI is a team of software scientists. These are software engineering experts, really who have expertise across the entire domain of molecular sciences, as well as several bona fide computer scientists and applied mathematicians on the team. The second major component is our cohort of software fellows. Right now, we're supporting more than 40 graduate students and postdocs all over the US. And we've supported, I think, 85 students and postdocs over the lifetime of the MOLSI so far. Our external advisory board is called the Science and Software Advisory Board. They're the ones who select the software fellows, and they have representation from academia, industry, national labs, and we have international representation on the board. And they give us advice and help direct us on the most important software priorities for the community. And of course, we have a set of community code partners, roughly 40 computational molecular science packages. The developers of these work with the MOLSI software scientists on developing standards, on developing training efforts and materials and software infrastructure. This is our current team of software scientists, 12. I won't go through everybody here, but suffice to say that they really do span the whole domain. Our most recent additions are Susie Latola, whom some of you may know, came to us from Helsinki, and Sina Mustafanejad, who just finished his PhD with Eugene DePrince at Florida State. Some of the software infrastructure projects that the team has been working on would be of interest to this audience in particular. The basis set exchange has been, I think, particularly high impact. This is an overhaul and expansion of the wonderful original basis set exchange that was developed at Pacific Northwest. And this has been really standardized and revalidated and is I think, going to be extremely useful to the whole community. Some of you are probably also familiar with the MOLSI's QC archive. This is an open community-driven database. It has a lot of different use cases, including large-scale data for machine learning activities, force field, small molecule force field development, and the like. And I'll also mention just here at the end, one of the things that we did most recently is the COVID-19 Molecular Structure and Therapeutics Hub. This is really a data and tool repository for molecular structures, models, and simulations that are related to fighting the COVID-19 pandemic. I encourage you to take a look at this. I think that this is of great use to a lot of folks in the community and an important service. This is our set of community code partners so far. If your favorite code is not here, we can fix that. Just we want as many people to work with us as possible on this, because we really want to help the entire community globally. This is a software fellowship program. As I said, we're supporting more than 40 fellows right now, and 85 we've funded over the lifetime of the program, and we're really pleased to be able to help these young people get started on their careers. Okay, so the MOLSI is a separate entity from my research group. So I'll come back to my research group now, since that's what I was going to talk about today, and talk about response properties. This has been a major focus of our work for quite a few years now, linear response properties in particular, but even beyond that as we move into quadratic response functions and further. Among linear response properties, you have really absorption related refraction, scattering, and emission. A big focus of our work has been in chiroptical forms of linear response, such as circular dichroism in absorption, optical or specific rotations, also known as circular birefringence, and refraction, Raman optical activity, and this is the chiroptical version of Raman scattering. And then circularly polarized luminescence is the chiral form of luminescence. And we're interested in all of these techniques. And all of them rely on response tensors. So for example, a key to all of these is the electric dipole, magnetic dipole polarizability tensor. This is a very sensitive quantity to calculate, but it plays a pivotal role in all of these forms of chiroptical response. And then there are others as well. There's the electric dipole, electric quadrupole polarizability. This is important not only for Raman optical activity, but also if you are determining optical rotation in oriented systems like crystals. And then, of course, there's the usual electric dipole polarizability. This also plays a role in Raman optical activity. We calculate these focused on couple cluster theory, the linear response theory form of that, where in this particular form, and I hope you can see my pointer, C and D are the property operators involved. So, for example, for the dipole polarizability, C and D would both be electric dipole operators, for example. And these depend on perturbed wave functions, that is field perturbed wave functions, that we obtain. These are, you can think of these basically as the derivative of the wave function with respect to an external field. That's the most straightforward way to do it. And you have to construct these perturbed wave functions for appropriate frequency pairs and every Cartesian component of whatever the involved operators are. So this is like resolving the couple cluster ground state equations over and over for different field frequencies and different perturbation components. And all of these come back together to connect back to the response tensors that I was indicating before. We avoid the sum over states computation of these because it is computationally too expensive and unstable. Instead, the linear response formalism allows us a way to get at least formally equivalent results, while instead of having to calculate every excited state, which is what goes into these sums, which is a gigantic diagonalization problem, instead we just have to solve systems of linear equations for the externally perturbed wave functions. And then we put all these together to calculate whatever tensors that we want. Right? And we do all of this within the Psi quantum chemistry package. This is, I guess I started working with Psi and becoming involved in development when I was actually an undergraduate, so we won't talk about how long ago that was, but the Psi package has evolved a lot over the many years. It is, I can indicate, this is an open source package. It's been open source for not quite 2 decades when we put this fully open source. It has, the current version, Psi 4, has a C++ infrastructure that allows us to do a good solid object-oriented approach, allows us to do faster development and easier maintenance. But the Python layer on top, I think, has been really key to the advance of Psi. Roland's comments notwithstanding, we found it to be extraordinarily valuable because it gives us a huge amount of flexibility. It gives users a huge amount of flexibility. And it's really been the ability to pass data and have clear APIs between the Python layer and the C++ layer has been absolutely essential. So a lot of wonderful capabilities. You can see a lot of what's going on in Psi in this paper that just came out a couple of months ago. And then you can also go to our GitHub repo or the main website to see how you can download and become involved if you're interested. So some of the recent work at Virginia Tech, I'll talk about a little bit of this. Some of the work we published here in 2019 on response properties, I'll get to in a second. We've had a wonderful collaboration going with Charlie Scott and Alex Tom at Cambridge in diagrammatic couple cluster Monte Carlo that I'll also talk about. And some of my work by my student Ben, who's an outstanding young student who will be finishing up later this year in some of his efforts in machine learning. Those will be my focus for today. Right, so Ruhi's work I'm going to talk about with local paranatural orbitals for response properties, Ben's work on machine learning for couple cluster properties, and then Roberto's work on diagrammatic Monte Carlo couple cluster. So probably most folks here are extremely familiar with virtual natural orbitals. This has been a concept that's been around for many, many decades in quantum chemistry. And the idea being that you build an appropriate, approximate, low-level one-particle density matrix at low level, meaning some simple level of electron correlation like MP2, and you build the virtual component of the one electron density. You diagonalize that density in that space, and the eigenvectors then become your new virtual space, except that you truncate the size of that space versus the original canonical Hartree-Fock space based on a cutoff value for the eigenvalues of that density, which are, of course, occupation numbers. So small occupation numbers you assume are not as important for the correlation treatment. You get rid of the corresponding eigenvectors, and that gives you a much more compact virtual space for your correlation method. The idea also is a component of the local paranatural orbital approach that Frank Neza and coworkers have wonderfully resurrected and expanded in recent years. In that case, the variation, of course, is that you are diagonalizing this virtual block of the reduced density matrix differently for each pair of localized occupied orbitals. So that means that you do the same truncation, but you're doing this for each pair of occupied orbitals that go into the calculation, which means you have a different virtual space for each pair of occupied orbitals. But otherwise, the concept of trying to reduce the size of the space is exactly the same, but in LPNOs, because you're tailoring the virtual space for a given pair of localized orbitals, you can really come up with very, very tightly compact and highly efficient correlation procedures. And these have been extremely successful for ground state energies, for example, and related properties. However, we have found that they're not effective for response properties because response properties, particularly chiroptical properties, are extremely sensitive to the quality of the wave function, not just the wave function, but also its derivatives, which, as I indicated before, we have to worry about the derivatives of the wave function with respect to external fields for linear and quadratic response functions. So one approach to this that we took was trying to build perturbation-aware virtual orbitals. So this is an extension of the LPNO approach that instead of using the original reduced density matrix, you now make use of perturbed densities for constructing the virtual block of this reduced density. So A here is supposed to be an external perturbation operator, for example, an electric dipole operator or magnetic dipole operator, and you build your perturbed density based on this and then follow exactly the same procedures. And we're using for these densities MP2-like forms for these. So this is basically the leading order contributions to the perturbed wave function, where I'm describing the perturbed wave function only by doubles. But once you've built this, again, for each pair of occupied orbitals, same as the LPNO approach, you diagonalize it using exactly the same procedure, and you have these are no longer exactly occupation numbers, but at least perturbed forms of these. And then you truncate based on some appropriate cutoff, and then associate the corresponding virtual orbitals with a given pair. That's now the correlating space for that pair. And so this gives you access to the same infrastructure that you already have for the LPNO approach, because really it's just the input density that's changing here, not much else. And so without getting too deep into the weeds on results, this approach in which we actually can take what we call a combined approach, in which we take the perturbed density and the unperturbed density and use a concatenation of those spaces, being careful, of course, to avoid linear dependencies between the orbitals. And we find that you can get both correlation energies and response properties right using this approach. And so, for example, if I look at calculation of polarizabilities, this is just for a small chain of hydrogen molecules. You'll see the now conventional P&O approach here Um, this is the polarizability compared to the black line, which is the canonical version. That's the right answer within the couple cluster approach, as a function of the cutoff used for the occupation number and the density. So a very low cutoff means that you're using a much larger fraction of the virtual orbital space, and you're not really trimming it very much, right? You're not so the right side of the axis here is inefficient, and the left side of it is extremely efficient, right? So for a cutoff of 10 to the minus 4, for example, you're using less than 10% of the original virtual space for each pair. And so what you see is that the P&O, original P&O, requires you to use very low cutoffs in order to arrive at the canonical form, to get your errors down low enough. But if you use this combined P&O++ approach, you basically are at the right answer from the very beginning. And that way you're using, it's a very small increase in the size of the virtual domain compared to a correlation energy only approach. Optical rotations are always more difficult. The P&O approach is all over the place, as you can see. The combined P&O++ it gives much smaller errors, even with very low cutoffs. So again, it's a very efficient method. This is probably the best candidate that we've found for developing a really reduced scaling linear response couple cluster approach. And so we're going to be pursuing this much more heavily going forward. Okay, shifting gears a little bit. So this has been Peyton's work, machine learning for correlated densities. We've been investigating a number of different machine learning approaches for trying to obtain couple cluster quality results from lower level models. And we started following work, the many-body tensor representation idea that Ho and Rupp published on the archive a few years ago. But Johannes Markgraf and Reuter recently applied this to couple cluster potential energy surfaces using Gaussian distributions centered on MP2 wave function amplitudes. So the feature set that they plugged in for their ridge regression approach was based on MP2 T2 amplitudes. And so they used a kernel or Gaussian-based ridge regression approach using CCSD level energies scattered across a diatomic potential, so bond breaking potential. These were the targets. And then the MP2 wave functions then, based on a training set initially, produced CCSD level energies based on MP2 level input. That's the idea. It performed well for a lot of these things. We found some interesting results in a recent collaboration with Johannes on this. For example, we found that it was highly symmetry dependent, whether or not you were utilizing symmetry in the calculation, in other words. And part of this was because of an issue with the implementation, in that they were basically choosing the first n large number of T2 amplitudes from the MP2 as the input data set, not taking into account that number of important amplitudes might change if symmetry were on or off. And this resulted in interesting kinks in the potential surface for carbon monoxide, for example, as you're pulling it apart. We decided to take a little bit different approach, again, in collaboration with Johannes Markgraf. We instead shifted over to using 1 electron densities, because these would provide a more compact representation than the wave function itself, and they would be potentially transferable to other molecules, which is an important target for this kind of work. Is having to retrain a model for every single application is not ideal. So we still use MP2 densities to construct these representations, using, again, CCSD potential energy curves as the targets for this. And we found that we can get away with very small training sets. It does not take a gigantic training set at all to nail down CCSD level quality. Here's the nitrogen potential surface, so stretching the triple bond in nitrogen. In this case, both the T amplitude tensor representation and the density tensor representation with a 20-point training set do really quite well. You have to really get down into a close view of this to be able to recognize the differences between the two. For something like lithium fluoride, though, you see these unusual kinks that occur in the T amplitude training that go away in the density tensor representation. And we have some ideas about why that happens. And then you can also apply these to other properties. That's an advantage of using the 1 electron density as a target for these, that you immediately get 1 electron properties out as well. So again, just 20 training points are sufficient for very high accuracy. These are absolute errors in the dipole moment for several different systems, including molecules like methylthiourine and methyloxyrane. And so this is really a proof of concept, and we're going to be investigating next about chemical transferability with localized MO or even AO type basis sets. And this is a collaboration with the MOLSI's QC archive team. And one last point about this, you can analyze the performance of these different machine learning models in terms of their training versus validation sets as a function of the number of training points. And what we see here is that really for both the T amplitude tensor representation, which is green, and the density tensor representation, which is in blue, this mean error as a function of the number of training points, neither is really going to benefit at all beyond 50 training points. And we see that the density tensor representation is basically maxed out at 20. So again, you really you have less bias in the density tensor representation, and you don't need a large training set to get these properties right. Okay, last is the diagrammatic couple cluster Monte Carlo. This is Roberto's work. It was a collaboration with Charlie Scott and Alex Thom, as I said before. We were interested in some of the wonderful work that had been going on in Monte Carlo techniques, the full CI, quantum Monte Carlo, the couple cluster Monte Carlo, and we recognized that there could be a great efficiency introduced in these, potentially massive reduction in the workload, if you represented the Monte Carlo steps based on randomly selecting specific diagrams rather than all the algebraic terms in the first place. And using a similarity transformed form of the Hamiltonian, make sure that you're only choosing linked components, which again means that you're not worrying on any cancellation of terms, as was the case in the original couple cluster Monte Carlo implementation. And so we implemented a prototype code that combines the Sci4 code and the handy package out of Tom's group to test this. And you have a selection scheme. Again, these are randomly selected at several different levels. First of all, you choose which component of the similarity transform Hamiltonian you're going to build a diagram from. You choose which Hamiltonian component you want, and then which T amplitude components you want, right? So this is a T1 squared times T3 contribution to triples. And then for that, you choose what particular connectivities and what particular internal, that is summation indices, and external indices you want. So all of these come together to form a single diagram. And I should be careful here. When we say a single diagram, we mean a particular number coming out, right? So not all the sums involved. We've chosen one element of all the internal sums and all of the external indices for one single number of the vast numbers that could go into play. And then you calculate a probability of the importance of this based on a number of probability factors. And that now represents one of the many diagrams that you've randomly selected. And then you iterate across these using a conventional Monte Carlo approach to eventually converge. And this is a highly parallelizable algorithm, but a key point is that its memory costs are vastly lower than the original couple cluster Monte Carlo and much, much lower than the full CI quantum Monte Carlo, which suffer from polynomial increases in memory due to they've sampled unlinked terms rather than even from the similarity transform Hamiltonian, they sampled unlinked terms instead of enforcing only linked terms, which is what we naturally do with a diagrammatic approach. And so here we've got these dotted lines from bottom to top indicate couple cluster singles and doubles, CCSD, then CCSDT and CCSDTQ Hilbert space sizes. And what you see is for the series of non-interacting beryllium atoms in this little test case, you can see that the diagrammatic couple cluster Monte Carlo, they maintain consistent memory levels, right? Because these are non-interacting, we naturally avoid any terms that would cancel out because they disappear from a linked diagrammatic approach. Whereas, for example, the full CI quantum Monte Carlo has huge memory costs associated with it. And this shouldn't be labeled memory costs. This should actually be computational scaling. So these are CPU costs and number of attempts at gathering stochastic samples from each step in the imaginary time propagation. And again, the CPU cost of the diagrammatic CCMC is really orders of magnitude less than the previous attempts at this same thing. And it's a much more parallelizable algorithm. So I will wrap up here as I'm approaching the end of my time. On the LPNO++ approach, this really is the most promising approach that we've found so far for reducing the scaling of couple cluster response calculations. And we're going to continue investigating that, especially at production level implementation. In the machine learning domain, we found that the density tensor representation, it provides significant improvement, or important improvements, I should say, over the T amplitude tensor representation. And we're trying to extend this work to not only additional properties, but also hopefully molecular transferability, but that remains to be seen. And then finally, the stochastic based diagrammatic coupled cluster Monte Carlo can potentially provide an alternative to more conventional techniques, in part because you've got low consistent memory costs for these, and it's a highly parallelizable algorithm. So we're interested in extending that work to molecular properties, including frequency dependent properties. And so this is thanking all the people who did this work, especially Roberto, Ruhi, and Ben, whose work I focused on today, and of course the people who paid the bills. And I will wrap up by noting the upcoming MQM meeting in end of June 2022 here at Virginia Tech. We're going to be honoring Martin Hedgorden and Gustavo Scoseria at MQM 2022. And I hope that this will come across. I'm going to show this because my daughter put this video together for me. I hope you can hear it too.